Now a couple of definitions, I'm sure you know about that, but of course now an oxidized compound is a compound that lost electron. A reduced compound is a substance that is gaining electron. An oxidant is a substance that is able to accept electron. So an oxidant will be reduced. A reductant is giving electron. So a reductant will be oxidized. We're talking about redox chemistry because it's always a coupling of two things. One is giving electron. Electron will not stay alone, naked in the environment, so you will have an electron acceptor. If you have an electron acceptor, you have a reduction. So an oxidation will always be coupled to a reduction. Let's take an example. Photosynthesis. Photosynthesis. Okay. What is a very simplified way of writing an equation of photosynthesis? You have H2O plus CO2 plus some solar energy from some energy from the sun will give you some organic matter that will simplify by writing CH2O plus some oxygen. This is organic matter if you want. I'm just simplifying. I could write glucose, for example. I would just simplify that. So this is photosynthesis, and this is a redox equation. Why? Because if you're looking at the oxidation state of the various elements in the various component, what it look like? Let's look for the carbon in yellow. CO2, we have seen that. Oxygen is -2, so the oxidation state of carbon is, in this case, +4. Oxidation state of carbon in the organic matter H2O, this is, in this case, 0, so it has to be 0. Here, what we have, oxidation state of oxygen in H2O, it's -2, we know that, H is plus, so and oxidation state of oxygen in O2, a pure substance, has an oxidation state of 0 by definition. So in our case, what we have is the CO2 that is an oxidized form of carbon that will be reduced into a organic carbon that is a reduced form of carbon. And we have the H2O that is a reduced form of oxygen that will give you O2, where if you have an oxidized oxygen. Again, this is about the difference in oxidation state. The oxygen in water is more reduced than the oxygen in the molecule oxygen, the oxygen, the molecular oxygen. The carbon in CO2 is theoretically oxidized compared to the carbon that is within an organic molecules. So photosynthesis is nothing else than a reduction of carbon into organic carbon and an oxidation of water into oxygen. So this is a redox reaction. You have a coupling of this CO2 into organic matter is coupled to the water into oxygen. So a reduction, in this case, this is a reduction. This is a reduction. This is an oxidation. We'll see a couple of other examples when we will talk about metabolism. Now let's look at the way to have the right stoichiometry when you're dealing with redox equation. And this is very interesting because it will also link the chapter 4 with chapter 5, because we will balance those equations with addition and subtraction of H plus, and H plus is a direct relationship with the acidity of an environment. So there's a set of rules that you will follow to balance a redox equation. There is different methods. If you know this one, and if you remember that, you will always be able to balance any redox equation, even if you don't do that for a couple of weeks or months. So what are those steps? The first one, of course, is to recognize that you have a redox equation. It's not an acid-base equation, for example, relationship or something else. The second one will be to write the two half reaction. The redox, again, what is oxidized, what is reduced. In our case, for the photosynthesis, carbon is going to be as half reaction. Carbon, CO2 will be reduced into organic carbon, and the second half reaction will be the oxidation of water into oxygen, O2. Then, for each half reaction, you will balance the main element. Without oxygen and hydrogen. So you have sulfur, carbon, iron, you name it. You're just balancing those elements. Then you're balancing oxygen by adding water on the opposite side, on each side that needs to be actually adding water. So oxygen, we will take an example, they will be clearer, but just fourth step is balancing the oxygen by adding water on the right side of the half equation, and for both half equation, by half reaction. 5 would be balancing the H, including the one you add with the H2O, by adding H plus. And then you need the 6 is the charge balance by adding electron to have both sides of half reaction balanced and neutral. And 7 would be to multiply each half reaction to have the same amount of electron on each half reaction. Then you will add the two half reaction and you will form your balance equation. Let's take an example. So let's take a couple of examples, and the results of a balancing equation will be different if you are in neutral condition, in acidic condition, or in basic condition. Let's take, for example, a neutral case. And just to prove that you can actually balance any equation, let's take a very simple one. We have copper aqueous with oxygen state of +2 is an ion, plus solid iron. So you're putting a solution with copper with solid iron in it. That will give you a iron 3 plus aqueous and precipitation of copper solid. So this is a reaction I'm giving you, and now I need you to balance this equation. If you don't know the charge, everything, it's look pretty balanced. You have one copper on each side, one iron and another iron on the other side. But it is absolutely not balanced in terms of charge, in terms of redox reaction. So now you need to first recognize the redox equation. Here in this case, if you look at oxidation state of copper, it's +1. Oxidation state of copper on the other side of the arrow is solid, is 0. So we have copper plus giving you copper solid. So this is, in this case, it's going to be in a reduction. And the iron that is solid will give you iron that is soluble, that is into water, and it is under the form of 3+. So this is an oxidation. So this is a redox reaction. The copper is reduced, the iron is oxidized. So let's now look through our steps. I'm writing the 2-half reaction. 1, 2. This is the reduction and this is the oxidation. So then I'm balancing the main elements without oxygen and hydrogen. Copper and copper balance, iron, one iron, all are balanced. Now I'm balancing the oxygen by adding H2O. There is no oxygen, I'm not adding H2O. Balancing now H by adding H+. There is no H, so I'm not doing anything here. Now I'm balancing the charge on each side. In this case, here I'm going to use a different color. Here we have a +1 charge, and this here we have a 0 charge. That means I need +1 electron here. Right. Now here we have an oxidation state of 0 here and an oxidation state of +3+ in here. That means I need to add +3 in this case. So now I just charge balance with electron. I need to multiply each half reaction to have the same amount of electron on each half reaction. We have 3 electrons here, we have 1 electron here. I need to multiply this equation here times 3 to have the same amount of electron. So I'm going to rewrite equation 1 here. 3 copper plus 3 electron will give you 3 copper solid. Now I'm simplifying this, and I can write by adding those two components together. We have Fa solid plus 3 copper plus will give you Fa3 plus 3 copper solid. And this is a stoichiometric balance equation, neutral. You don't creating any acidity, you're not creating any basicity. So no H, no OH in this case. This is an example in neutral setup.